Recording. All right. Okay, so today what I'm doing this morning is just to run through again the main topics that we covered in the course, just to refresh your minds and sort of assist in you focusing on the revision itself. And if there are questions that you have coming up, just let me know as we go through. All right. We'll have a face-to-face. My plan is to have a face-to-face tomorrow with you all, where I'll give you back, you'll get back your midterms, and we can go through the solutions there. And similarly for ECNG 2012. Okay, but we have to kind of wait and see what happens with UE as well in terms of access to campus tomorrow. All right, so let's begin. So we had in all, there were a total of 28 lecture lessons throughout the semester. And what I've done here is I kind of group it more or less in this, well, in the order that we did it and then by topic. All right. So the first 6 lectures that we had covered general signals and systems operations. Of course, we covered things like what exactly the purpose of the course was and the role of signals and systems in the whole scheme of things that you all will be doing. And we started off by some, after doing that, we started off with some simple signal operations, which you would meet all over the place. And especially later on when we started to do things like convolution and so on. And the main operations were time scaling, which dealt with things like compression and expansion, time reversal, which of course was to take the signal and reverse the time order of the signal, and time shifting, which was to delay or advance the signal with respect to time. All of this we spoke to in the context of both continuous time and discrete time signals. In time reversal and time shifting, it's much easier to reverse a discrete time signal in time because it's stored data and numbers. So you just have to play it back in the reverse order, like audio or video recording or something of that nature. Similarly for time shifting, that you could sort of jump into the middle of the stored data for discrete time, and you could go backward or forward, or you could send it backward or forward. And the analogous example that I brought to you all was like a shift register. In a shift register or a counter, for that argument, if you have an 8-bit count and the count is at some point, you can either reverse the count or you could shift the count, which is to delay the count down. Like with a shift register, it delays, right? And you could also advance, which is to bring it forward in time. All right. Continuous time is not that easy to do because reversing a continuous time signal, unless you have continuous time recording, which does exist, right? The old-fashioned tape recordings, for instance, you could reverse and you could play. Well, you could reverse and play it backward, and you could also, by jumping into the middle of the recording, basically advance or delay it as you see fit. After we did that, we saw that in because of the fact that in engineering we meet any number of signals, it's impossible to test and classify every system to every type of signal that it will meet. So what we did is that we realized that there are certain special signals that basically, if we know the behavior to those special signals, we can kind of we can deduce what the behavior is to virtually anything else that the system will meet. And as we saw later on, because of relationships like the Fourier transform, where any signal is broken up into a set of sinusoids, if we know the sinusoid response, for instance, for a system, then if I have some funny looking signal that goes into the system, because of what we know about the Fourier transform, this is composed of a whole series of sinusoids. And if we know the response for each of them, right, because of what we know about sinusoidal behavior, then we can deduce what the behavior to the composite signal would be. All right, and the important special signals that we looked at were of course, I'll come to the impulse in a little while, the unit step, which is like an on-off, so nothing, and then at time 0, it turns to 1. The ramp, which is nothing, and then at time 0, it increases at a rate of 1 unit per amplitude for 1 unit of time, or any linear sort of relationship of that nature. It could also decrease, as we saw in other places as well. The sinusoid, which you know is either a sine or a cosine, right? They're the same signal, just one is a shifted in time relative to the other. And then, of course, this character called the impulse. The impulse was a funny signal in that it occupied 0 time, t equal to 0, but the height, the magnitude of it was infinity. So that was undefined, but we defined it as an integral where the area of the impulse was 1. Right, so the power, the weight, or the energy behind it was 1, and those were the main signals, and we based our entire conversation on that. So we looked at this step and the impulse response all the way through. The sinusoid, we spent on several sections, several lessons when we were talking about frequency responsive systems and so on. And the ramp we met sort of in between, not deliberately around the place, but it occurred when we spoke about things like convolution. It occurred elsewhere in another course when we spoke about creating what do you call it, signal triangle waves, where you took a unit step and you integrated it. Okay. At any time, if you have any questions, feel free to call. I may see it on the chat, but you might have to drag my attention by saying something. All right. Right, so we went through this, the properties of the unit impulse. The main great property of the unit impulse is this thing called the shifting property. If you remember, the shifting property said that if I took any signal and multiplied it by the unit impulse, what it did was to extract the value of the signal at the point where the unit impulse occurred. So like a delta t is at t equal to 0. So it's going to extract the value of the function at t equal to 0. Similarly, if you put the impulse at some point in time t equal to 50, if I multiply ft by that, it's going to give me the value of the function at t equal to 50. And we use that to talk about sampling, where we said, okay, so if I could find a series of impulses spaced in time uniformly, each of them is going to extract a single value of the function. So if I have a whole sum of these, it's going to extract a whole sum of values from the function, which is what sampling was about. Right? And we draw a little circuit with a multiplier, and we had some questions if I vary the sampling rate and so on as well. Then we spend some time speaking about piecewise continuous signals. Those occur when you have an instant where the transmission of a signal disappears. So the signal is going along, and then you lose contact, and then the signal reappears, continues, and you may lose contact again. How do you handle that? And we saw that these sudden changes, if, for instance, you were passing this through something that was finding a derivative, every one of these sudden changes is going to give you an impulse of some sort. And impulses create responses in the system that it has to handle. And we knew that. Well, we expanded on that when we spoke about impulse response and so on a little bit later on, right? Which is right here. And the impulse response, basically, those two signals, the impulse and the step, challenge a system to the max. It asks the system to respond to its limit of behavior. In the case of the impulse, you are imposing a very short duration but very high amplitude signal onto the system. What does it do? And in the case of this step, you have nothing going on, and then you suddenly turn it on. What does it do? And that kind of response tells you certain things of them. And you met this in previous course as well. You get something called a steady state response from it, and you get the transient response from it, right? So steady transient, which is when you put a signal, a step input into something, it does some sort of behavior, right? It's behaving, and then it settles down. This behavior where it's now, until it settles down, this thing when it's going from nothing to some final value, is changing, or it's in transient mode, right? And after it settles down, it stays in an unchanging state for a while, which we call the steady state. Yeah. Okay. Excuse me for half a second. Right. And then we looked at some operations that we introduced in between up until this point, but a little bit more formal. Causality. Oops, there we go. Back a bit. Causality. Causal systems are those systems that start at some time t. Before that time, nothing happens. After that time is when the system is working. And we normally designate the start time as t equal to 0 for us. Causal systems are good because they are predictable. All right. If the system is not causal, it means at the point in time when you start to look at it, there's some history going on before. And at that point, you have to figure out now what are the conditions of the system before you started to look at it. And a case in point we said is for example, a power supply. If you start to look at the power supply is off for a while, but if it's a good power supply, the filter capacitor will be holding some sort of voltage value. So when you turn it on, it will give you an output voltage that is not necessarily the full output voltage. It will start at some level and then settle down. The other one was memory. Does the system have elements that store voltages? Capacitive and inductive elements store values. They remember the energy in them for a while, so that when you start off the system, the system may not start at exactly 0. Time invariance. The time invariance part was what, if I did something today to our system, and I did the same thing tomorrow to the system, I'm supposed to get the same response. It doesn't depend on when I actually put the input into the system. All right. Linearity was basically that if I made a change of 5 volts on the system, I got a particular sort of response on the output. If I made a change of 10 volts on the system, I'm supposed to get a proportional change of maybe twice the 5-volt change or something of that nature. That the input-output relationship basically, if you look at the input-output relationship, the input-output relationship is some sort of straight line. So that if this is output and this is input, a change in the input here responds in a change in the output here. The same change in input at some other operating point will result in the same magnitude of change in the output. Okay? If nonlinear have this kind of behavior, right, where a change in input here results in this sort of change in the output, but the same sort of change in the input somewhere else in the condition makes a much different change in the output. That is nonlinear. You're going to meet those kind of systems, but what you do is that you try to operate within the linear range. And then bounded input, bounded output means that we want systems that we have a limit on what is the size of the input we could put in, and we also have a limit on what is the size of the output that it can give. Right? If it's an unbounded output, it means it can literally explode on you, or it can overload a power system and it can cause damage. as the case may be. So you don't want that at all. So we deal exclusively with linear time invariant systems. We understand that in some cases they may or may not be causal. If they're not causal, we need to know what we call the initial conditions. Right? And linear time invariant, that the time invariance, the linearity in there is taken. The memory, of course, sort of ties back to the initial conditions. We basically want the system, if the system has a memory or it is not causal, we need to know what is the initial conditions. And then on top of all of that, we need to know what are the limits of the inputs and outputs. All right. And those 6 lectures concluded our look at signals and the sort of characteristics that we'll expect. And we use these terms going forward all the way. All right. Then we spent 3 lectures now going through a review of the Laplace transform, because you had done an entire course on it, which is ECNG2011. But what I try to do and what we try to do here is to put it in context. So from our perspective, first off, what were transform techniques? The transform techniques, of course, were mathematical tools that allow us to take a difficult problem, and by using the transform, we carry it into a place where it's easier to solve. And then we do the manipulations there, we do the solutions there, and then we come back to our time zone. The Laplace transform is one such transform, and we met 2 others during the course of our lectures. We did a quick review of the Laplace transform. We usually use it to solve differential equations, because, as we saw, all engineering problems, the shorthand for describing any engineering system is a differential equation. How you solve that is difficult. So we have this tool that if we know certain things about the particular system, we can apply this tool called the Laplace transform and convert it into a different form. That form now allows us to solve the behavior of the system, and also to predict how it works. So in some cases, while in the Laplace domain, or what we call the S-plane or the S-domain, right, you can see certain things now about it. First off, we know from the Laplace transform, we got the representation of the system, and we got something called the transfer function. And the transfer function, remember, is the impulse. You take the impulse response of the system, the Laplace transform of that is what we call a transfer function. And the transfer function has some solutions. Remember, it has a numerator and a denominator. All of them are functions of S in the S-plane or in the S-domain, right? The roots of the numerator we call zeros. The zeros are where the system will tend to shut down. The roots of the denominator are what we call poles. And the poles of the system are where the system tries to go to its maximum output. So at this point in time, we didn't know what we know later on, but it's a balance of poles and zeros that sort of keep the system operating. One set of values are trying to shut the thing down, the other one is trying to put it up to its maximum output. So the balance of the poles and zeros determine how the system works. And you're going to spend your control systems courses, those of you, well, of course, the compulsory course next semester. And if you go on to do advanced controls, you're going to spend time looking at the pole zero placement in terms of how the system works or not. And then we saw, well, wait a minute, if I just want to find out certain things, like what is it when I put something into a system, what does it do when I now turn it on? Does it exceed its design value or not? And then after it's been working a while, does it settle down to the value that I want or not? So we make use of 2 theorems called the initial and final value theorem that give us that information without having to solve anything. So you take the transfer function, you put the input that you have on it, usually a step input, and then you look and see what does it do when it now starts, what does it do after it's been settling down for a little while. Okay. then after we did that, now we went on now to talk about, we spent 2 lectures talking about something called convolution. First off, what was the meaning of it and the derivation of the relationship? And what we saw is that any system, any LTI, remember system, any LTI system whose transfer function in time is h, if I put a continuous time signal into it, xt, and I get something coming out of it, which is yt, that the relationship between y, x, and h was what was a convolution equation in time, that yt was equal to xt convolved with ht. And this, in fact, was an integral, right? X tau ht minus tau d tau, right? And you're basically running all the way through to see, to evaluate this. We derived it by looking at discrete time signals first, and then we and we concluded the convolution relationship. And then we expanded it now and said, okay, if the discrete time signal became in such a way where the values were closer and closer together, then eventually it became a continuous time signal. And that's how we got the behavior and derived a relationship for the continuous time integral that we have. And then after that, we remember this, that what is convolution? Convolution is a relationship between the input, the system, and the output for all linear time invariant systems, okay, in time. We saw that, okay, that yes, you know from the property of the Laplace transform that ys is equal to x s h s. That's fine, and you can evaluate the convolution by a multiplication. But what if xs wasn't easy to come by? So for instance, a simple thing like a rectangular pulse, a start and a stop, defining that in terms of the Laplace transform is you have a step, you have another step that is a negative going step, and the difference between the two of them. So even getting the Laplace transform of this to evaluate it here is challenging, and it gets more complex if the system, something looking like this, for instance. If I give you something looking like this, defining the Laplace transform of that is not particularly easy. You have to deal with some steps, you have to deal with a ramp and so on. And then if I ask you to find a convolution of that with another piecewise continuous signal, then you run into little issues there. So we saw that for certain situations, it might be easier to do it in a manual form. So we spent an entire class looking at that and then doing some examples. There were many examples there in the notes and in the problem set and now in your past papers where with solutions, so you can go through that. And if you have any questions, of course, between now and the exam, we can run through them fairly quickly and easily. What we spent time on were the easier, quote unquote, ones where you have square and rectangular pulses being convolved with each other. Just now, excuse me a second, please. All right, yes, I had to take a call there. Right, so we did the convolution with some simple signals first, square and rectangular pulses. And of course, we did variations of that where the pulses were the same length or different lengths. And then if they started at 0 or if they were shifted up and down. Looking at the results from the midterm, most people seem to have gotten the idea correct. Right, so we're on a good place there. If there are things that you still don't understand and you're trying problems and you're not getting it out with the solutions that are around, let me know. Do the example, send a scan for it, and I will comment on it and look and see if I can clarify it for you. And then we did some more complicated ones where we had rectangular or square pulses, and we were finding the convolution with things looking like this, you know, those kind of things. The biggest issue with that is, of course, you have to find the equation of these lines, right? Some people still having little issues with that. You just have to remember how, go back to your calculus. How do I find the straight line, the equation of a line looking like this? You know this slope is negative. You look for the intercepts and you find the equation, okay? And again, we have some examples like that are around. So we spent 2 lectures on that. Then we spent a lecture looking at first and second order system responses, which are very different. The first order impulse and the first order step response. A first order system does not have any type of oscillation in it. When you put the impulse response, for instance, a simple RC circuit, the capacitor charges up to some value and then discharges. You put a step into it, the capacitor will charge. We put a step voltage here. A first order system will try to respond by giving you, again, nothing before, and then it will try to respond by giving you something looking like that, right? It eventually settles at the input of the step in, the value of the step input. In some cases, if you have resistances around and so on, it could settle below it. Or in some cases, if it's just taking, if the capacitors, for instance, in the circuit are large, you could get this thing just going on for a very long time. The point is that it never crosses the value of the step input. So you put a step, if you have a step value here, the output never goes past that. Okay. Then we looked at the step impulse and the step response and the impulse response for a second order system. Remember, a second order system, whatever you have something, the transfer function has a s squared plus in the denominator. So you have 2 poles. And what happens to that now is that both the impulse and the step response, you get behaviors where the system can go beyond the input. And in the specific case of a step input, we saw that the second order system could give you this, it could go from this extreme all the way up to this kind of behavior, right? So it can overshoot, it can go here, it can settle down and so on. And because of that, the system is capable of oscillating. The second order response leads to complex poles. Complex poles or complex solutions in the Laplace domain, you know, leads to cosines and sines. So sinusoids oscillate. So once you have a second order system with complex poles, you're going to have oscillation because it's sinusoids and cosines that are created. And then whether the sinusoids or cosines die out is a result of another thing that we saw called damping. And then we saw the standard form of the second order system, which is something that you have to memorize, which was the A omega naught squared over S squared plus 2 zeta omega naught S plus omega naught squared. The natural frequency here, the omega refers to the natural frequency, and damping refers to this factor here. The closer zeta is to 0, the more the system oscillates. The closer it is to 1, the more it tends to behave like a first order system. A, of course, is just a system gain. All right. Good. And then now, once we were finished that, and there were examples that we did, there are a number of them inside of there included, and we'll revisit that shortly as we do the Fourier section of the course as well. We expanded on this a bit. But remember this, you need to have this at your fingertips usually. Then we looked at modeling. We emphasize the fact that what we're doing here is tools for modeling. The real system, you can't build a system if you have a challenge. You can't build a system by putting motors and amplifiers and power supplies together in one shot. So what you do is to develop a model. And the tools that we use are some of the things that we meet in this course. And one form of modeling is to use a block diagram representation. And we started to do that, and we introduced a concept of feedback, and both positive and negative feedback. And we saw that if I have a simple feedback system, right, the forward block has a transfer function G or S, the feedback block has a transfer function HS, right? If the feedback was negative, which is the kind of feedback that we want to control and settle on a system, that the transfer function was G over 1 plus GH. If the transfer function, if the feedback was positive, which you want in some cases, but not generally, not all, right? Then you get G over 1 minus GH. All right. And then using these results, we were able to simplify block diagrams. So you have a complicated block diagram. Usually simplifying it involves shifting around things. So you have to shift takeoff points to before and after blocks, or shift summing points before and after blocks. You can't shift a summing. If you have a summing junction and a takeoff point, all right, so this is coming from somewhere, this is coming from somewhere else, and you have a takeoff point, you can't swap the order of summing points and summing junctions and takeoff points. But you can move these before and after blocks. You can move these before and after blocks. You can swap the order of takeoff points. You can swap the order of summing junctions, because as we saw, things like A plus B minus C is the same as A minus C plus B, and so on. So you can mix it up to your heart's content. But remember, you can't swap the position of the takeoff points and summing junctions. And using that, there were examples that we did in class. There are examples in the past papers and in the problem sets and so on with solutions. There was also one in the in-course, and you'll get that back tomorrow. If not, if we can't meet, you will be getting the solutions for the midterm as well. All right. Many people did quite well on that. In some cases, it got a little long, and they couldn't simplify. They left their answer in an unsimplified form, but at least they were on the right path for it, which is good. Right. And then there was a special case that that is a bit of a homework issue, so that the answer is to prove that the transfer function for this system that has two inputs into it has this sort of form. And the way to do that was, first off, because we're dealing with linear time invariant, we can use something called superposition. Right? So what that means is that, first off, look at the two inputs. So let ds equal to 0. Set that equal to 0. So you have that. What is this? So what is y1 equal? That is the one where ds equal to 0. Then you go back here and you set r equal to 0, and you get a y2s. And then if you substitute it, and then you add the two of them together and simplify, you're supposed to get this answer down here. All right? It's straightforward. In one case, with, notice in this one, with rs equal to 0, notice that the block diagram has some positive feedback in it. All right? When ds is equal to 0, we have negative feedback in it. Just redraw the diagram and you'll see how it works. Okay, this minus sign, if I set this equal to 0, I still have a minus sign coming in here. So you have nothing minus this. So in fact, ES will will still have a minus sign in it. So try it, see what you have. The solution is there because I've given this in the past papers already. So the solution is around. So if you're trying it and you're not getting the answer, again, please let me know. All right, so that was the answer there. Right. Then we spent a good chunk of the course, lectures 15 to 22, covering the frequency domain, which led us into the whole Fourier series and Fourier transform part of the system. First off, we saw that signals have a time response, but the time response is like looking at a chair from the front, right? Depending on your orientation, you can't tell if the chair has 4 legs or if one is broken and hidden behind the other one. So looking at the frequency domain is like looking at the same thing from another angle. So you get a different perspective. Both of them give you equal insights. And we saw that, like in the case of the sinusoid, a sinusoid looking like this in the time domain, in the frequency domain would have a single frequency component at some point. So we looked at that and we expanded, and that gave us this understanding, that a conceptual understanding of what the Fourier series was, in that you could take any periodic signal, and that was important, that concept, any periodic signal, and that you could break it up into sinusoids and cosinusoids. And that was the whole rationale behind it. So back to what we had said before, if I know how a system works for a sinusoidal input, then for some arbitrary signal, I know that the arbitrary signal, because of its Fourier series components, is broken up into a series of sinusoids. So therefore, I could deduce what the behavior of it would be for all of the sinusoids that it's likely to encounter. All right, the Fourier series applied to periodic signals. You did a big part of a course in ECNG 2013 on Fourier series and all the various manipulations, odd signals, even signals, and so on, and how to find the Fourier series for all sorts of things. And how to do that is part of that course. It's not part of this one. So finding the Fourier series for a triangle waveform or a sawtooth and all that kind of thing is not part of our syllabus here. What we needed now is to use that to go forward, because our concern was moving forward from there into something called the Fourier transform, which is, for our purposes, a bit more important. So what we said is that the Fourier series is a slightly different form of it because of the relationship between the complex exponential and the complex exponent e to the j omega and cosine and sine. So you can express the Fourier series in a very compact form called the complex exponential form, right? And this form also has a resemblance, even at this stage, to what you know in the Laplace transform. The integral looks the same. And then we used it now to find some, we started to discuss things like spectrum, which is the frequency content of a signal. And we use a complex exponential form on an example signal to get its DC and its harmonics. And that made us, and that eventually led us also to our first encounter of something called the sinc function, which is a sin x over x function. All right. And one important thing that we saw is that the continuous time Fourier series give a discrete spectrum. In other words, the spectrum is a function of k omega naught. Omega is a fundamental frequency. So it will tell us what is at omega naught, what is at 2 omega naught, what is at 3 omega naught, and of course, what is at DC, which is 0 hertz. All right? It doesn't tell us, the Fourier series continuous time doesn't tell us anything about what's happening at 1.3 omega naught. Right? You're not going to get anything like that. You're going to get 0, 1 omega naught, 2, 3, etc. Right? A discrete spectrum always. And then we said, okay, well, let's play around a little bit. What if I were to take the Fourier transform and, the Fourier series, and try to find the Fourier series for a signal whose period is huge. And that led us now to derive something called the Fourier transform. The look of the Fourier transform, the version that we saw was for all intents and purposes the same thing like the Laplace transform. We integrate between 0 minus just before 0 and infinity xt e to the minus st dt. For the Fourier series, we integrated between minus infinity and infinity xt, sorry, for the Fourier transform, e to the minus j omega t dt. So on the surface, the form of the integral was very similar. What you had to watch was, of course, the lower limit. The Fourier transform sums from or integrates from minus infinity. And then in one case, you have e to the minus st. In the other case, you have e to the minus j omega t. Right? So it already gave us a little hint that the behavior and the use of the Fourier transform could be fairly similar to the what you already knew about the Laplace transform. So we looked at that. There were similarities and differences, right? The main difference, of course, because of this summing from 0 and this summing from infinity, is that if you try to find the Fourier transform of something like a unit step, you can't simply just take the Laplace transform and make the substitution s equal to j omega. You forget it, that omits a behavior, which is what happens at DC or 0 hertz. All right, so we did all of that. We did the Fourier transform of an impulse, which gave us we saw the frequency content, which is the Fourier transform of the signal, was infinite for an impulse, which is why it's such a when you put an impulse onto a system, why the system has such a significant response to it. Then this step, we derive that. Then we did the Fourier transform of a pulse, and that's where we met the sinc function again. And we did a pulse. So the pulse was 1 over a, minus a over 2 to plus a over 2, and the height is 1 over a, so that the weight or the area, just now, half a second. Okay, the office, but it got disconnected. Right. So we saw that the Fourier transform of a pulse led again to this sinc function, and that we could create an impulse if we made, as we made A get closer and closer together, then the weight, it got closer and closer to a unit impulse. And we saw this sinc function with this sort of thing here, drawn badly. Its amplitude is 1. And that these crossing points were proportional to the width of the pulse. So as A got larger, these points are proportional to like 1 over A. So as A gets bigger, these points get move further and further apart, right? And eventually get the it's proportional to A over something. So as these points get larger, this 0 crossing here moves further and further apart, and the spectrum eventually flattens out. All right. There was a homework question on the Fourier transform of a trigonometric signal, and it's in problem set 4 with the solution. Right. So again, as we get, if issues come up, I will try to answer it, and I will see if we could get some online revision sessions going as well to deal with the problems as they come up. And then we also saw that you could also use the Fourier transform to solve a differential equation, just like it would be with the Laplace transform, except that there were no initial conditions because the Fourier transform sums from minus infinity. So you can't have an initial condition there. Okay? Then some of the conclusions here, the Fourier transform, remember the Fourier transform leads to a continuous spectrum, unlike the, what do you call it, the Fourier series that gives you a discrete spectrum. This one, the spectrum of the signal is going to be nice and continuous. And then after that, now we spent a couple of classes talking about how do I estimate the Fourier, the frequency response of a system. So if I give you a transfer function HS, how do I plot what the behavior in terms of omega looks like? And this is where we came across this thing called a Bode plot or Bode plot. And what we do is to use straight line approximations to give us an overall behavior. And we did a number of examples in that, how it works. We express it in decibels. Decibels means that the responses are log. And if the responses are log, it means that things that are multiplying normally, when you take the log of them, they become additions. So we can draw these straight lines around the place and then just add the straight lines up together. There were 9 examples that we did for various things, from zeros to simple zeros, to simple poles, to poles and zeros. And I also, in the slide, showed you the command in MATLAB, how to check it. So you can, the MATLAB will give you, of course, a continuous plot, but you can check your straight line answer against the solutions inside of there. And then we spent some time looking at what happens to equations with complex poles. We remember the complex poles, and that is back to this one, the A omega 0 squared over S squared plus 2 zeta omega naught plus omega naught squared. Depending on the value of zeta, you get complex poles, right? And so that's damping. And depending on the value of the damping, you get a response that will give you this. And remember, second order systems decay at minus 40 dB per decade, second order. And if zeta gets very small, then what you get is you get a magnitude rise right at the corner frequency here. And we went through how to calculate it, how to calculate the magnitude rise. And the type of questions that I told you I could ask you, and you will see in the past papers and so on. I could give you a figure like this and tell me what was the transfer function. So you have to look at this point, you have to look at this point here, you have to look at the resonant frequency here, and from that you could derive the transfer function. Or I could give you the transfer function, and from it you can tell me an estimate, right? So you could calculate what this point is, you could tell me what this point is, the resonant frequency, you could tell me what this value is, and you could sketch it. Okay, so I have given both types in past papers. You'll see them appearing in the examples with solutions that you have posted. Again, any questions, just let me know. Stability, there were two lectures on video recordings that I asked you to look at. Basically, the idea was, how do I tell if a system is stable? And if the system is stable, you have the transfer function HS is equal to some numerator over denominator polynomial. Depending on the roots here, which are the poles, if the poles have negative real parts, in other words, if this is a S-plane, this is sigma j omega, so every S is equal to some sigma plus j omega. If the real parts, and you know this from your Laplace transform answers already, if the real parts are negative, meaning lying across here, then the system is stable. The problem, of course, is that how do I get the poles of something? If I give you something like S to the 5th plus 5S to the 4th plus, and so on. Solving this without MATLAB by hand is tedious. So this is where this technique called the Route-Hurwitz stability criterion technique came about, and it's explained. There's a tabulation technique. You get something called a characteristic equation, which is when you do the thing, the 1 plus GH part of a transfer function here, you tabulate the value. So this is again going to give you a S4 plus 3S squared plus 2S plus 1. You tabulate it, so you put the highest order, you put the coefficients first, and then you go down by 2. So it's like 1 and 2. Then S cubed is 3 and 1. And then you complete the table for S squared, in this case, S1, S0. And the recordings and the slides explain how to do it. All you have to do is not make mistakes. It's just algebra. And then you look here. Everybody in this first column has to be greater than 0. If it is not, the system is unstable. And the number of sign changes tells you how many poles are misbehaving. All right? And there were 3 cases to deal with. Right, when you do your tabulation, if nobody in this column is 0, we want everybody positive, remember that. If one person is 0 and everybody else has a number, or if the whole row is 0, what to do? Okay, and the slides have the examples to work on, and they were gone, they were taken through in the video. And also, every year you get past paper questions, so you will see them as well there. And then a little variation that I showed you is that sometimes the characteristic equation, I could give you a characteristic equation, and inside of the characteristic equation has some unknown variable called k. And if you work out the route through its criteria, when you look at the first column of the table, you will have, some numbers, and then some function that is a value of k. And you have to look and see what value of k inside of here makes that function greater than 0 for stability, or less than or equal to 0 for instability. Okay, and there are some work examples on that, and a number of questions available for you to go through as well as part of your revision. Okay, and then the last thing that we spent some time on was discrete time system. We spent 2 weeks on that. Introduction to them. Discrete time systems deal with something called difference equations, which are analogous to the differential equations for the continuous time case. We need another tool to solve. Normally, it would solve the difference equation by something called recursion. But instead of doing that, that is tedious. The Laplace transform can't work for that. So we came up with something called the Z transform. And the Z transform was a power series, right? So you get the samples, Z to the minus n, and you're summing from 0 to infinity. Right, so x z is equal to that. It is a power series, so you could, if you know the values of x and t, you could just write out the answer. Right, it's a power series of z minus 1, right? Power, so it's z minus 1 to the power n. Right, so it's going to start at 0, at 1, then 1, and then something z minus 1, then z minus 2, z minus 3. And remember this, z minus 1 means 1 over z, literally, okay? And we did the usual thing. We found the examples of z transforms of impulses and steps and exponents and so on. We introduced something called the region of convergence and the unit circle. There is the z transform for the power series here to converge. And you remember that from your calculus and your add maths, that a series will only have a sum to infinity under certain conditions. In this case, in the Z transform, it relates to something called the unit circle. The region of convergence is either inside the unit circle or outside, right? So it's either here or here. And stable systems, you want to have the poles inside of here. You're going to meet that in your controls, not here, but it's just a no. Okay, unstable systems are outside. And then our focus was on two properties of the Z transform, which were analogous to the differences here, analogous to the derivatives in the continuous time domain, right? Where you had a SY, S, right, minus Y 0, etc. It's the same sort of behavior that we had here. So the properties, and we went through that. There was a there's a work class example on the slides with the solution, and then a number of them. Every past paper has an answer in one in there to work out with solutions. So we did that, and then the inverse Z transform. There were two ways. There are actually three, but we only use two. One is long division. So the transfer function GZ is a numerator transfer function by a denominator in Z, right? And what you do, you divide the numerator by the denominator, and it gives you the first few values. So if you do that, you could get the inverse Z transform for the first few values. Or if you want to find a closed form, then you put this in partial fraction form. So you get a over, you know, something minus Z minus 1 plus B over, you know, K minus Z minus 1, etc., etc. Solve for A and B. Remember that Z minus 1 is a variable. So I suggested to people, if you're not comfortable with this, you could let something like M equals Z minus 1. So something like 3 over 1 minus 4Z minus 1 becomes 3 over 1 minus 4M. So you could solve for everything in terms of M, and then go back to make the substitution again and look up the answer in the tables. All right. Okay, and that is where we ended the course. As I said, everything, there are questions and solutions for everything that we've done right now. Tomorrow, if we get access to the campus, I'm bringing back your in-course, so we'll run through that, and we could take some questions on things that people might need clarification and so on. As we go through in between, if you have issues, I will sort of collate the problems and so on, and we can have an online session or 2 or 3 as the time allows to go over problems. If you're working and you can't wait for some session and so on, feel free to just tell me what the issue is, send me a scan, and I'll respond as soon as I get it, as soon as convenient, I'll respond with an answer to you. All right? So fair enough? Everybody all right? If you've been following the work, you have the slides, you have the recording of the Monday lectures, you have the recordings from before, right? Some of them are a little bit better than others and so on, of a whole bunch of materials inside of there. So if you've been at least, you know, following the class up to that point, you should be all right. Okay. Some of you all have a little more work to do in the final exam. Remember, the final exam is 80%. So if you didn't do too well in the midterm, you have a good chance again to get through. All right. You know how much you have to get, and don't try to pick and choose topics. Cover the stuff that we did. If there are things that need clarification or things that you're a little bit weak on, now is the time to spend the time and get the clarification on it. Just do the practice, do the past papers and so on, and we should be all right. Okay. All right, I went a little bit over here. Sorry for that. So let me stop the recording.